Hello. So this is going to be a quick lesson on vectors. And so what is a vector? In the past, we have been playing around with the definition of distance. And where we became a little bit limited was when we started graphing an object as it was, traveling in position over time. All of a sudden, we could have an object that was traveling with a positive slope. You could have an object that's traveling with a negative slope. And so we really need this tool to incorporate direction so that we can better describe our object's motion. What does that have to do with vectors? So what a vector is I previously introduced to you guys the definition of distance versus displacement. Distance is a scalar, meaning that we just have a value associated with it. Whereas displacement is a vector, meaning that it has the value, but it also tells you what direction your object is moving in. And so that's going to become important because it will better, define that. So it has both, let me see if I can use this annotating tool, it has both magnitude and it has direction. Now, if we take a look at vectors, geometrically, we draw them as arrows, where the length of the arrow is the magnitude of the vector. The arrow is useful because it's pointed off in a direction, right? And there's a tail to the arrow and there's a head to the arrow as well. Now, oops, let's see if I can delete those. Okay. Now, where that becomes important is when we start needing to add vectors. So let's say we have an object, and I'm going to annotate this. Let's just say that this is, this is our north. Right? And let's say that this is our east. Okay. So let's go on a walk. So object A, or you go walking northeast, which is the A vector, right? Then you decide that you're going to walk southeast, and that would be the B vector. Now we can add those two vectors up, and quantity-wise, so if you did, the magnitude of A plus the magnitude of B, that would be your distance. And if you think to, say, Google Maps, for example, that would be really useful. But oftentimes we want to know, right, and there's a special operation called vector addition where we can add the two vectors, and that will give us what's called the displacement. Now, a vector A plus B is our displacement vector. So that is how we have moved through space position-wise. And so we have a special word for that, and that's called the resultant vector. Some terminology. If you just have an object that's moving, notice that velocity is also a vector, which we'll define a little bit later. But let's say that this object, is, again, we're moving in the northeast direction. It's going off, right? And here is our resultant vector, if you will call it, because you'll see that it's the addition of these two components. So this is where vector addition becomes important, is that, say that we're just talking about one object that's moving, and I only give you the resultant vector. Well, it's important to know that at all times, even though we have this resultant vector, you'll be able to know that it is traveling some amount solely in the x direction, and it is traveling one amount solely in the y direction, and the addition of those two, they add up to the resultant vector. So we call that the x component, and we call that the y component. And there could be an angle, right? Usually we'll use the Greek letter theta, though you may see the Greek letter phi pop up as well. And you could probably kind of see where this is coming to. In the future, I'm going to give you a resultant. And what your job is going to be in the future is to say, okay, let me build a right triangle out of that and solve for my components. So in the case of the triangle previously, our x component was the adjacent side, and our y component was the opposite side. So if I gave you the resultant vector, which was the hypotenuse, well, lo and behold, as long as you know the angle and you know the resultant, well, you can solve for those components, which will become much useful later when we move into two-dimensional motion.